It's chemistry and you are watching Chem Science.
We have already discussed question 1 and 2 of question paper 419701 chemistry of the examination series October-November 2023, and now we are going to discuss next two questions, that is question 3 and question 4. So here is question 3. Hydrogen peroxide is a liquid at 298 Kelvin. It is moderately stable under room conditions but will decompose quickly if a catalyst is added, and the reaction is given here. A balanced reaction is already given here, and the first sub question says define entropy. So entropy, I'll say entropy in the very easiest word, is a measure of disorder of a system. You can also write it's the way of measure of different ways of arrangement of particles in a system, but for me entropy, this is the best and easiest definition we can remember, that it's a measure of disorder of a system. It says predict the sign of a standard entropy change of reaction 1. Explain your answer, sign and explanation here. So if we have a look at the reaction here, it says there are two molecules of hydrogen peroxide in the liquid form on reactant side, and on product side there are two molecules of water again in liquid form, but then there is one more molecule of oxygen which is in gaseous form. So you can say that the sign is a positive. Why I'll say? Because for entropy change we always do products minus reactants entropy if you want to find out the entropy change of a system. Reactants, I'll say. So entropy change of a system will be positive if the entropy of the products is bigger, and here you can see that entropy of products is bigger because already there are two molecules of water just like reactants on a product side, but additionally there is one more molecule. So more the number of molecules, more will be entropy, and plus if a molecule is in gaseous form, the gaseous molecules have more entropy than the molecules of liquid and solid. So additionally there is a molecule of gas also. So explanation is that there are more number of molecules present on product side, and there is a gas molecule. Because of that the sign of entropy change becomes positive. Let's go ahead with the next part of the question. It says some bond energy data are shown in table 3.1, and here are the table given. Use the data in the table 3.1 to show that the enthalpy change for the following reaction is minus 196 kilojoules per mole, and the reaction is given here. So if a reaction is given here, first we need to find out what are the different types of bonds present here. So first let me show you the types of bond. If there is hydrogen peroxide, the structure of hydrogen peroxide is this, and there are two molecules I have written 2 in front. So this is the reactant side minus the product side. Now on the product side there are two molecules of H2O. So H2O is OH like this. So you can say there are two molecules of OH. So I can write it like this, 2OH, plus there is one molecule of oxygen. Now oxygen molecule is O double bond O. So this is the product side. So if we want to calculate, this is how we are going to substitute the values. 2 into you can say 2 bonds of OH, 2 bonds of OH are here. So 2 into 460, 2 into 460 plus again this 2 goes for one more bond, that is O single bond O. So let's write that also, 2 into the OO, that is O single bond O bond energy, that is a 150, that is 150. This is how I'm writing, and minus the reactant side. Now OH bond is 460, which we have already written here. So again we have to write 2 into 460. Plus now again O double bond O is 496. Now though it's 1 mark, we need to show the whole calculation. So enthalpy change, that is delta H, is calculated this way. So okay, let me correct here one more part, is that here there are already 2 OH bond present plus multiply by 2. So the multiplication here should be 4 into 460, and the same goes here. There are 2 OH bond already present in the water plus multiply by 2 here. So here should be the multiplication of 4. Here is a correction where I'll correct it, and this 2 multiplies to the O single bond O here, and the O double bond O is already 1 molecule here, so no need to multiply here with any number. So this is how we are going to substitute the values. And if we all multiply and add all, we get minus 196 kilojoules per mole. This is how we get the answer. So this is how we proved that it's already minus 196 kilojoules per mole. Okay, here is the next sub question. It says some standard entropies S are shown in the table 3.2. So the entropy of hydrogen peroxide is given, that is positive 102, and entropy of water is plus 70. The enthalpy change and Gibbs free energy change for the following reaction is also given here in kilojoules per mole. Use the data given to calculate the standard entropy of oxygen. Oxygen here is the oxygen molecule given here. The enthalpy change delta G, delta H is given, and the entropies of 2 molecules also given. Now the formula which we are going to use is delta G standard is equal to delta H standard minus T delta S. Now if we are doing this, now if we substitute all the values given here, now we need to check whether the units shown are same or not. You can see that the enthalpy change is also in kilojoules, and the Gibbs free energy is also in kilojoules per mole. So no need to change. But if entropy here is given in joules, not kilojoules, so we'll have to work accordingly. But then let's first substitute the values given here. Now let's see the temperature. What is the temperature used? It's already given in the question above that it is happening at 298 Kelvin. 298 Kelvin. So let's see here. Yes, it's given here 298 Kelvin. So the temperature taken should be 298 Kelvin here. So let's substitute and find out the value of delta S first by substituting these values. So delta G is minus 238 is equal to minus 196 of minus 298 into delta S. So this ends up as delta S is equal to 42 upon 298. This is how we get, and the answer is plus 0.141. Now this is the total entropy change of the system. Out of that, hydrogen peroxide and water is already given, so let's find out it out for oxygen. Now here let's understand that this is the value which we have obtained in kilojoules per Kelvin per mole, but then we know that the values here given is in joules, so we need to convert it into joules by multiplying this by 1000, so we get 141. Now the total entropy change is 141. That should be equal to the entropy of products. Now what is the entropy of products? We already know that water and oxygen are the entropy of the products. So water is plus 70, so we need to multiply it by 2 because there are 2 molecules. So 2 into 70 plus the entropy of oxygen minus the reactant side. So reactants we have 102 for hydrogen peroxide, multiply by this 2. So 2 into 102, and then after substituting and rearranging the equation, we get delta S oxygen. Delta S of oxygen is equal to 204.5. sorry, it's 204.9. So this is how we get the entropy of oxygen in joules per Kelvin per mole. Remember here the entropy we had received, we had calculated was in kilojoules, which we converted into joules by multiplying it by 1000, and that's how we get the answer. Let's go ahead. It's written, the decomposition of hydrogen peroxide is catalyzed by aqueous iron 3 chloride and by silver metal. Identify which of these two catalysts is acting as a homogeneous catalyst. Now what is homogeneous catalyst? Homogeneous catalyst is a catalyst which is in same state as the reactant. Now out of these two, aqueous is iron 3 chloride and silver metal is a solid. Now the reactant is hydrogen peroxide, which is again in aqueous state. So obviously iron 3 chloride is in same state, homogeneous state as the reactant. So homogeneous catalyst is iron 3 chloride, and the explanation which we is going to write is simple, that it is in same phase as reactant, that's how we write it, and it's as simple because it's just 1 mark. Let's go ahead with the next sub question. The sub-question E says the electrode potential values for two electrode reactions are given here, and the two electrode reactions are hydrogen peroxide acidified turns to water molecules, and Cr3 plus chromium 3 plus electron gets reduced to Cr2 plus, and the electrode potential values are given here as positive 1.77 voltage and negative 0.41 volt for the two half equations. And the sub question following is, an electrochemical cell is constructed with the following half cells: an acidified solution of hydrogen peroxide and a platinum wire, chromium 2 plus mixed with chromium 3 plus, and a platinum wire. Identify the positive half cells and calculate the standard E cell, that is electrode potential value of the cell made by combining these two half cells. Obviously the positive half cell is the one which has a bigger positive value, that is the hydrogen peroxide has a bigger positive value compared to the other half cell. So the positive half cell is the hydrogen peroxide half cell, which is acidified. And E cell value, if you want to calculate, that is bigger minus smaller, that is 1.77 minus of minus 0.41. that is how we calculate the E cell value. So we get plus 2.18 plus 2.18 voltage. After addition of these two values we get 2.18. So this is how we calculated the E cell value. And the next is calculate the value of delta G for the cell reaction that occurs per mole of hydrogen peroxide. The formula to calculate delta G is minus NF E cell value, and we know F is Faraday's constant, that is 96500. The number of moles of electron that should pass through the half cell. So if we calculate here hydrogen peroxide and chromium, the number of electrons that should be passing through, the number of moles of electrons that should be passing through the circuit is 2 mole, because if we make and full equation from this, we'll need to multiply this by 2, and so each of the species will get 2 moles. So here 2 moles of electrons are passed through. So if we substitute the value minus 2 into 96500 into the E cell value, which we have already calculated, that is 2.18, and we get answer as minus 420.7. The units are already written, kilojoules per mole. And the next sub question, the electrode potential values for two electrode reactions are given, that is hydrogen peroxide acidified half cell is already given, and the same values here. Another half cell is made of cobalt 3 plus plus electron gives cobalt 2 plus, and its electrode potential value is plus, that is positive 1.82 volt. An electrochemical cell is constructed with the following half cells. Half cell 1 is an acidified solution of hydrogen peroxide under standard conditions and a platinum wire. Half cell 2 is a solution containing 0.02 moles per dm cube cobalt 3 plus and 2 moles per dm cube cobalt 2 plus and a platinum wire. Use the Nernst equation to calculate the value of E, that is electrode value of half cell 2 under these conditions. So according to Nernst equation, the Nernst equation says that the new electrode potential value will be E naught plus 0.059 upon Z into the log of the concentration of oxidized species upon the reduced species. This is the formula. So if we have a look for the cobalt, which is the non-standard conditions, the E cell value for cobalt is 1.82 volts. So that will be substituting here 1.82 plus 0.059 divide by 1. What is Z? Z is the number of electrons passing or used for this particular equation half cell. So here only 1 mole of electron is used. So divide by 1 into log of concentration of the oxidized species. Now the oxidized species is CO3 plus because that is more oxidized and its concentration is 0.020 upon the concentration of reduced species, that is cobalt 2 plus, and its concentration is 2.0. So we'll divide it by 2.0. This is how we are going to substitute the value and calculate the new value of E. And the answer is plus 1.702. So if we write it into 3 significant figures or 3 decimal places, it is plus 1.702 voltage. Let's see what's next. Says write an equation for the cell reaction that occurs in this cell under these conditions. So first see which is the bigger value and which one will go in a forward direction. So if we have a look at the two half equations and the cobalt in a new conditions, then the E value is 1.702. Now that is also smaller than the value of hydrogen peroxide, that is 1.77. So in that case the forward reaction will be for the acidified hydrogen peroxide and the reverse reaction will be CO2 plus that is of cobalt. So CO2 plus will be reactant and CO3 plus will be the product because CO2 plus will get oxidized. So if we combine the two equations, the hydrogen peroxide reaction, okay, let me write it this way. Hydrogen peroxide reaction, that is H2O2 and 2H plus plus 2H plus, and as we have already seen, cobalt 2 plus is the reactant and we need to multiply it by 2, as I have already shown you here that there is 1 electron to balance. We'll multiply the whole equation by 2. So we'll get 2, 2 and 2 moles on each of the species, and so CO2 plus multiply by 2, that are 2 moles are the reactants, and on the other side we have 2 moles of water plus 2 moles of cobalt 3 plus. So this is the overall reaction. I hope this is clear that as the hydrogen peroxide E naught value, electrode potential value, is greater, that's going to be the forward reaction, and the E value of the cobalt, the new E value in the new conditions, is also smaller than the hydrogen peroxide value. So that is the reaction which will go in reverse. So that's why we have taken CO2 plus as reactant and CO3 plus as a product, and that's how we have combined the reaction to make one full equation. Let's go ahead, and the next equation is define enthalpy change of hydration. So enthalpy change of hydration is the enthalpy change when 1 mole of gaseous ions, 1 mole of gaseous ions dissolves in water to form a dilute solution. That is the definition of enthalpy change of hydration. Let's see what is next waiting for us. It says aluminium fluoride AlF3 is an ionic compound. Complete and label the energy cycle to show the relationship between the enthalpy change of solution of AlF3, that is aluminium trifluoride, lattice energy of aluminium fluoride, and enthalpy change of hydration of Al3 plus and F minus ions. Now what they have done here is they have given you 3 boxes. They have given you the enthalpy change and there is only one arrow given. Now if we are talking about one arrow, we should know from what is going to make what. Now if I start with aluminium 3 plus ions, aluminium 3 plus ions in gaseous form plus F minus ions again in gaseous form, and it forms AlF3 solid of ionic compound, then I need to balance this, and obviously this is lattice energy, enthalpy change of lattice. Now if we are talking about solution, then AlF3 if undergoes an enthalpy change of solution, it is going to form Al3 plus aqueous plus 3F minus aqueous. That's how it's going to form, and this is the arrow direction I'll show, and this is the enthalpy change of solution. Now if you talk about hydration, as we have already written in the definition, that gaseous ions undergoes the dilution, that is it dissolves in water to form the aqueous solution. So this is going to be the hydration, where the gaseous ions are dissolving to make a solution, and the arrow direction should be this way. This is how it's going to make the whole cycle. You can also change the position of all this. The condition applies that the direction of the arrow should be correct. Only one direction arrow is given, the remaining two you have to make. So it totally depends on you. You can definitely change the position, rotate it one more time and write the positions correctly with the correct enthalpy change name. Here they have written relevant data for these questions are given. Use this data and your energy cycle in G2 to calculate the enthalpy change of lattice for aluminium fluoride. So if we want to calculate the enthalpy change of lattice energy, then the formula is enthalpy change of hydration minus enthalpy change of solution. So if we talk about enthalpy change of hydration, we have to consider both the aluminium and fluoride ions. So enthalpy change of hydration, I'll directly substitute here minus 4690 kilojoules for aluminium. But for fluoride ion, we have to multiply it by 3. So 3 into minus 506 kilojoules per mole. Now this is enthalpy change of hydration of both the ions minus enthalpy change of solution of aluminium fluoride, that is minus 209, and so this is how we get the enthalpy change of lattice. Hydration, we have considered both the ions, and fluoride we have multiplied by 3 because we have taken 3 fluoride ions. So this is how we substitute the values and calculate the answer for lattice energy, and the answer is minus 5999. So that's how we are going to write it, minus 5999 kilojoules per mole. Here ends the question 3. Let's go ahead with the question 4 also. Question 4 is cobalt 2 nitrate, that is CONO3 twice, is a reddish brown crystalline solid. It dissolves in water to form a solution containing cobalt H2O6, that is hydrated cobalt 2 plus complex ions. Now the complete table 4.1 giving the formula of cobalt containing species that is formed in each of the 3 reactions described. Now when to the cobalt hexa aqua cobalt 2 plus, I would name it like that, hexa aqua cobalt 2 plus, when NaOH is added to it. Now if you remember the reactions which are given in our syllabus, If OH minus is added to water molecules of the ligands water molecules to cobalt complexes, two of the water molecules gets replaced by OH. So I should start writing cobalt. I'll write OH twice because two of the water ligands are replaced by OH and the remaining water molecule stays as such, that 4 ligands remains as such. Now if we talk about the charge of the complex is 2+, and we have added twice OH minus ligand, so the overall charge for this also goes 2 minus. So cobalt charge is CO2 plus and the charge of the OH is again 2 minus, so it's get neutralized and so there is no charge of this complex. If we go ahead with the next amine ligands, the complex containing amine, that is ammonia ligands, are more stable, so it's going to replace all the ammonia are going to replace all the water molecules, and so we'll get NH3 and as ammonia is a neutral ligand, the charge of the cobalt CO2 plus stays on the charge of the complex also. Now when concentrated HCl is added, chlorine is going to replace water molecules, but then chlorine can form only the tetrahedral complex, that is Cl4 is only added. H2O6 is replaced by 4 chlorine ligands. Now the charge of the chlorine is minus, so if 4 chlorine are added and the cobalt has a 2+ charge, so -4 and 2+ will overall give a charge of -2. So I'll write the charge of the complex as 2-. So this is how you get a new complex with the chlorine ligand. The next sub question that follows is describe the color change seen in reaction 3. Now in reaction 3, that is this one, the reaction 3. Now if your original color of cobalt, that is hydrated cobalt, is pink, so we'll write it pink. And when these ligands replace chlorine, it changes to blue. So this is the color of the complex. It's fixed and we need to remember the color of the complexes for each. There is no other way out. So remember, the hydrated cobalt, that is the water ligands of the cobalt, gives the complex pink color, and when it's replaced by chlorine, it gives it blue color. The next is calcium nitrate. Calcium nitrate is a white crystalline solid. When heated, it starts to decompose at approximately 500 degrees Celsius. Write an equation for the decomposition of calcium nitrate. So when calcium nitrate undergoes thermal decomposition, it forms calcium oxide, nitrogen dioxide and oxygen. So these are the three products we get. And now if we talk about balancing it, we need to put 2 here, 2 here and 4. This is how it's going to balance the equation. Let's go ahead with the next sub question. Says suggest the temperatures at which magnesium nitrate and barium nitrate starts to decompose and explain your answer. Now if we talk about magnesium nitrate, barium nitrate and calcium nitrate, they are all group 2 nitrates, and group 2 nitrates, then the magnesium comes first, calcium and then barium comes. And if we talk about the trend of decomposition, then we should know that the decomposition temperature increases down the group, so barium nitrate decomposes at a higher temperature. So if calcium nitrate decomposes at 500 degrees Celsius, barium nitrate is going to decompose at a higher than 500 degrees Celsius, and so you can write any temperature crossing 550. I can write 580 degrees Celsius, and magnesium nitrate should be lower than 500, so I can write it approximately 400 or 410 degrees or anything related. So approximately 420 to 450 you can write. There is no other problem. For the explanation, I'll suggest that what you need to write is that as the cation size increases down the group, as the cation size increases down the group, increases down the group, the ion polarization decreases. Ion polarization decreases. This makes NO bond stronger. NO bond, I'll better write it this way, NO bond stronger. If this NO bond stronger, it needs higher temperature for decomposition, decomposition of nitrates down the group. So higher temperature for decomposition down the group. So that's how I'm going to write the explanation for 3 marks, because this question carries 3 marks. Let's see what is next. Next sub question is question 5. The question 5 is also about transition elements, and it says transition elements behaves as a catalyst and can form complex ions. Explain why transition elements behave as a catalyst. Now the first thing is, to behave as a catalyst, it should have a variable oxidation state. But why the transition elements have a variable oxidation state? You need to explain, because it carries 2 marks. So if they have variable oxidation state, it's only because the d orbitals of transition elements, are vacant to form dative bond or coordinated bond. You can write even the coordinated bond, dative bond with the ligands, and it also have variable oxidation states. So these are the 2 points we need to explain why they behave as a catalyst. So the next is, silver forms a linear complex with cyanide. Copper forms a tetrahedral complex again with the cyanide. Titanium forms a complex TiCl4 diaz 2, where diaz is a neutral bidentate ligand. Now understand, diaz are bidentate ligand. State the oxidation state and the coordination numbers of titanium in TiCl4 diaz 2. Now if diaz are 2 twice, and they each diaz form a bidentate ligand, that is forms 2 coordinated bonds. So total 4 coordinated bonds are formed by the diaz, and 4 more for the from the chlorine. So total oxidation state of Ti we can calculate is that the charge of the diaz is 0, the charge of the chloride is -1. So overall charge given by the chlorine ligands is -4, and the titanium, here you can see it's a neutral. There is no charge on the complex, so that shows that the titanium should have a +4 oxidation state. Otherwise also you can calculate by substituting the value as x for titanium, for chlorine -4, for diaz 0, and the overall charge is 0. So that's how you can calculate the value of x, and you get +4, +4 as an oxidation state of titanium's x value. Coordination number, as we have already seen, 4 bonds from chlorine and 4 bonds from diaz, and the total 8 bonds are formed. So the coordination number is 8. Now draw a 3-dimensional diagram to show the shapes of silver forming the complex with the cyanide, and copper also with the cyanide in the boxes. Now already they have told you that the copper forms a tetrahedral and silver forms a linear complex, and it also says label 1 bond angle on each diagram. So what I suggest is Ag plus Cn. We can show the bonds of Cn, otherwise we can directly write Cn, another Cn molecule like this, and we also need to label one of the angles. So I'm labeling it as 180 degrees because it's a linear, so the angle should be 180 degrees. And for copper, it's a tetrahedral structure with Cn. And if we show a three-dimensional structure, then one of the lines should be bold line. So this is how I'm going to draw a bold line for one of the Cn ligands. So this is Cn, and one of the line is dotted for the fourth Cn. And if we label the angle for a tetrahedral complex is 109.5 degrees. So you can label any one of the angle as 109.5. In the MS, you can see they have allowed 109 to 110 also. So that is also acceptable. The numerical value for the stability constant of copper 1 complex is 2 into 10 power 27. Write an expression for K stability of copper cyanide 4,3, it is 3 minus. So now understand, copper has in charge of +1 and Cn has in charge of -1, and it's formed the complex. So if this is the complex, then if you write a equation for this is, then it's going to form from its copper ion +1 plus 4 Cn minus ligand. So this is how you can write. So the stability constant, you know, we have to write products on the top. So on the top our product goes, that is Cn 4 times power 3 minus. So this is the product, and in the denominator we have the reactants. So reactants Cn minus, but then as Cn has the stoichiometry of 4, so 4 goes in the power. So this is how we write the stability constant expression. Now as we have seen, this 3 minus is just the charge, not the power. So I'll put one more bracket, and where I'll show no power because 3 minus is the charge, not the power. So I'll put one more bracket to show that 3 minus is the charge and not the power. Let's see next. In a solution, the concentration of Cn minus and copper cyanide complex are both 0.001 moles per dm cube. Use your expressions from C1 and the value of K stability to calculate the concentration of Cu plus in this solution. Now the K stability value is already given, that is 2.0 into 10 power 27. So 2.0 into 10 power 27. Let's check, it's minus 27 or plus 27. Yes, it's positive 27 upon the concentration of the product. Now the concentration of product is 0.001. So 0.0010 divide by the concentration of copper ions as such, and the Cn minus is also 0.0010, but that has got the power of 4. So if we substitute the value, we can get the concentration of copper 1 ions, which is 5.0 into 10 power minus 19. Obviously it is 1 marks, but remember students, I always keep on telling my students that never ever calculate the answer directly in the calculator and write. You need to show the expression, substitute the values correctly in the expression, and then write the answer, because the steps showing calculation also carries marks. Now there is one more question following. Says a piece of copper containing alloy has a mass of 0.567 gram. It is dissolved in an acid giving 100 centimeter cube of a blue solution in which copper is Cu2 plus ions. An excess of potassium iodide is added to 25 centimeter cube sample of this solution. Now remember, we had a total of 100 centimeter cube, out of which we have taken 25 centimeter cube of the solution, and Ki, potassium iodide is added to this solution. All of the copper is precipitated as white CuI. So the reaction is given here. Ki is added to the copper solution, which is 100, out of which we have just taken 25, And we have got copper iodide. The liberated iodine here is then titrated with 0.02 moles per dm cube of thiosulfate solution in this reaction 2. So here is also the reaction given. Calculate the moles of iodine that are reduced in this titration. Now, if you have a look at this reaction, the volume and concentration of thiosulfate solution is given, and the stoichiometry of the iodine and the thiosulfate is 1:2. So, moles of thiosulfate is double the moles of iodine. So, if we want to calculate the moles of iodine, we need to divide the moles of thiosulfate H2O3 2 minus divide by 2. So we get the moles of iodine. And how do we calculate the moles of thiosulfate? Concentration multiplied by volume. So what is concentration? 0.02 multiplied by the volume, that is 20.10 into 10 power minus 3 I did to change the centimeter cube into dm cube, and then divide by 2. The answer is 2.01 into 10 power minus 4. Okay, calculate the moles of copper in the original piece of alloy. Now, if you have a look at the moles of iodine and copper, it is the copper ions are twice. So again, the moles of iodine has to be multiplied by 2 to get the moles of copper. So let's calculate the moles of Cu2 plus. That is 2.01 into 10 power minus 4 multiplied by 2. Now you must have understood why did I multiply by 2, because compared to iodine the moles of Cu2 plus are double. But then remember, we took only 25 centimeter cube of copper for the titration. The total volume was 100. So actually the moles of copper is 4 times the moles which we have calculated here. So again multiply by 4, or you can just cross multiply that 100 divide by 25. That also you can do in place of 4, but I did it directly multiply by 4. If you don't want to do this, we can say multiply by 4 divide by 25. That also will do. And the answer is 1.608 into 10 power minus 3. That is the moles of copper ions, that is Cu2 plus ions. Now calculate the percentage of copper in the alloy. Now to calculate the percentage of copper, first we need to multiply the moles with the molecular mass of copper. Now if you have a look at molecular mass of copper in the periodic table, that is 63.5. So the moles of copper, that is 1.0608 into 10 power minus 3 moles into molecular mass, that is 63.5. Now divide by the total mass of the alloy. Now what is the total mass of the alloy? 0.567. So divide by 0.567, that is the total mass of the alloy. So this is the mass of copper. Divide by total mass of alloy into 100. That will give you the percentage of copper in the alloy. And we get an answer of approximately 18.0%. So percentage of copper in the alloy is 18%. Now suggest why a solution of Cu2 plus is colored but the solid CuI is white in color. Cu2 plus have an empty d orbitals available for transition of d electrons. Now d electrons transfer from the lower d orbitals to higher d orbitals, and that is only possible when there are empty d orbitals. But in Cu plus ions, that is Cu plus, or we can write CuI ions, there are no empty d orbitals, there are no empty d orbitals available for d electrons transition. So that is the reason that whenever we have the transition elements with empty d orbitals, they will be colored. But if the orbitals, d orbitals, are not empty for these any transition metal ions, then the compound won't be colored. So Cu2 plus compounds are colored, but Cu plus compounds are not colored. And this is how the question 5 also ends. Let's discuss the next questions in the next video.